Okay, nice. Thanks. Okay, so hello everyone. Today we have Asaf Cassel presenting his work with Aviv Rosenberg on linear MDPs. And Asaf Cassel is like a fifth-year PhD student at Tel Aviv University, working with Tomer Cohen. And prior to that, he was working at the TechUn. His research interests primarily lie in reinforcement learning theory, as you could guess, with an emphasis on like non-tabular problem settings, so such as like the linear ones, as he's going to talk about today. So Asaf, thank you for coming, and you can start.
All right, thank you for having me. I might as well also add that I'm currently also dabbling to some extent in RLHF as a research student in Google, but so it's also something nowadays. Right, so let's dive right into it. So today I'll talk about warm-up free policy optimization, which is improved regret and gives improved regret in linear Markov decision processes. And this is a joint work with Aviv Rosenberg. So like reinforcement learning has had a lot of empirical success, whether it's in robotics or in games or nowadays in language models. And as we know, generally our goal is just to learn a good behavior policy via interacting with the system. All right, but generally speaking, RL is still pretty hard to train, even though all of these successes. And as I assume everybody here knows, we're still working on theory in the hope of improving this. So like the sort of most basic hurdle to the basic theory is that typically the state space is huge, and so we would like to have some sort of function approximation, because using tabular approaches that consider the state to be finite is not very practical. So in this sense, we would like to introduce some function approximation, and the simplest case for this, which is mostly studied in the theory, is the case of linear function approximation, and this is what we'll be looking at today. So before I dive into the setting, so like what's been done so far. So this setting of linear function approximation was originally introduced by Jean et al. And they introduced a value iteration type algorithm that considers stochastic costs and bandit feedback and gives like this square root of h to the fourth t to the third k regret. A later work used variance reduction methods by he et al. To improve the dependence on h and d to the optimal dependence. But more recently, there were also some works on policy optimization. So Sherman et al. Suggested a policy optimization algorithm that can work either in the stochastic bandit feedback case or adversarial full feedback case. And they achieve the square root of k dependence, but they get a bit of a degraded dependence with respect to the function approximation decision horizon h. K is the number of episodes. And finally, I'll mention a work by Leo et al., which studied the hardest case where you have adversarial bandit feedback. And here, at least efficiently, we still don't know how to achieve square root of k regret. We can only get this k to the 3/4 regret. Sorry for the weird notation. Okay, so the case that we'll be looking at is a similar case to what Sherman et al. Were looking at. So we'll be looking at either stochastic bandit feedback or adversarial full feedback. And what we'll show is a new policy optimization algorithm for linear MDPs. And we'll be achieving a regret rate which is virtually equivalent to the case of value iteration like Jean et al. Achieved. Okay, so square root of h to the fourth t to the third k. There is this additional term which is sort of a mixed term, but I would say that for the most part it would be smaller, or at least equivalent. And this, as the main thing, it improves the dependence on H and D compared to Sherman et al.'s work. And generally speaking, it would probably be the best rate that we can expect without variance reduction methods. And what we'll show is that we use a type of contraction mechanism, which will avoid a costly pure exploration phase that Sherman et al. Needed. Right, so a bit of technicalities on the definition of the setting. I'll try and go through this relatively fast because I assume this is mostly known, but if anything's unclear, let me know. This is the general definition of MDP. So we have a set of states X, a set of actions A, an initial state X1, which is without loss of generality, just a single state. And we have our loss functions. We'll be looking at losses here as opposed to rewards. So it's worth noticing because it might be confusing in some cases. So we're trying to minimize loss rather than what's often the case, maximize reward. And we have this transition function P, which is just the probability of transitioning to a next state X, given that we started at a state X and take action A. And we'll be looking at the finite horizon problem where the decision horizon is capital H. Okay, and for this, the classic linear function approximation setting is what's known as a linear MDP. And for this, we parameterize the transition function and the losses as linear functions of a known feature map phi. Okay, so we assume phi is a known feature map, and the unknown parameters are these psi's and thetas. So the thetas are pretty reasonable. They're just like d-dimensional vectors. However, the psi's are actually like mappings from S to RD. So this actually gives relatively large degrees of freedom. Okay, it's not something we can actually hold in the memory of the system because it's the size of the state space. But as is known, nonetheless, we can learn efficiently in this situation. And finally, what we are actually interested in is the adversarial linear MDP, where now the losses, instead of being fixed or stochastic, they can change arbitrarily from round to round. So we'll denote them with an additional index of k, okay, indicating the episode. And in the case of linear MDP, the parameters of the loss function can again change from round to round, so they also get an additional index of k. Lost my trail of thought for a sec. Okay. All right. So for this setting, the interaction protocol is the standard protocol where we have an episodic setting. So at each episode, our agent needs to choose a policy pi k. Subsequently, they'll observe the entire trajectory that they traversed, so all the states and actions that they went through. And then if the feedback mode is the bandit feedback, then we only observe the losses that we actually incur per decision horizon. And if it's full feedback, we observe the full loss function. So in the case of the linear MDPs, we simply observe these thetas directly. Okay, and this is the setting we'll be focusing on today. So everything I'll say basically works for stochastic losses, but we'll focus on the adversarial case. And the quantity that we want to minimize here is the standard notion of regret. So it's the difference in value between our policy and the best policy in hindsight. Okay, and the value is again the usual notion of just the expected loss through the H decision horizons with respect to a given policy. Right, final technicalities. Okay, so just to recall, so the value function I already mentioned is just the expectation of the sum of the losses. But in general, we'd like to define the usual value function for a horizon H. So this is simply the value function from step H, given that we start from state X. And also we have the Q function, which is the same, also conditioning on the fact that at step H, we take action A. And for these two, we have the usual Bellman equations. So the important part is just to remember that the Q function is just the immediate loss plus an expectation over the next value. And the value is just taking the Q function and taking expectation over the action with respect to the policy. So standard stuff. All right. So finally, we can dive a little bit more into what we actually want to talk about, which is how to do basically policy optimization for MDPs in general, and eventually, of course, for linear MDPs in particular. All right, so sort of the naive approach for this, if somebody is not familiar with policy optimization, is sort of a bandit approach. One might say, okay, let's just discretize the policy space, right? At least in the tabular case, you can do it sample complexity-wise and calculate the value function for each policy in this discretization and look at this as an expert problem and run like multiplicative weights or whatever algorithm you would want, and sample policies from our discretization using these weights. Okay, and the regret for this would be very easy to bound when the system is known. Okay, so you can just use a concentration argument to show that the regret is exactly this loss of the expert problem. Okay, so this is just the probability of choosing the policy, which is the expert times its loss, compared to the best loss in hindsight. And you can run OMD and get a regret of square root of k log the number of experts. It's hard to see where am I in the outline?
It's okay. Can you just not navigate with left and right? Maybe that's a silly question.
What?
I was just asking if you can just navigate on the slides, just pushing left or right.
Yeah, I was hoping that would be. Oh, okay, left and right. I was trying up and down. Okay, great. Left and right.
Okay.
Thank you for that.
Okay, I guess my actual question was going to be precisely about what you have on the slide regarding the number of experts that you get with this approach.
But yeah. So sort of obviously this is a very naive approach, and the number of experts would be exponential in the size of the state space and H, and so this is of course not a very great solution. It just shows you that sample complexity-wise you can achieve something, but that's not really what we're aiming for. We want to get something efficient. So what's been shown before is that what you can do is sort of local policy optimization, and this is sort of the common approach. Okay, so now at each episode, you're starting with your current policy pi k, and you need to calculate its Q function at each state, action, and decision step. And now you're running sort of this expert algorithm per state. Okay, so now you're looking at running OMD per state with respect to the actions. Okay, and your loss is just a Q function. And now this just outputs a simple stochastic policy. Right, and the regret analysis for this, again, would be quite simple. So you can use a standard value difference lemma to get that the regret is exactly this OMD loss per state. Okay, and you can bound this per state, and now you get that the regret is actually h squared k, square root of k log a. Okay, and now this is actually efficient. Okay, so you can compute this and everything's fine. But this is just for the case where the model is known. Okay, of course, what we're interested in is the case where the model is unknown. So sort of the naive thing that you would do is just simply estimate the model. And now instead of calculating the true Q function, which you could do before, now you need to estimate it, and you would have to have an optimistic estimate. Okay, so optimism would generally entail having an estimate, since this is losses, that is smaller than the true value. All right, so the standard way that you would do it again is the losses were given after each state, so we don't need to estimate them. We will reduce from them a UCB style bonus, which we'll explain later, and we'll replace the value backup step, which is trying to calculate the expected next value, with just an empirical version with an estimate. Right, and the next value is still calculated as usual, just as an expectation with respect to the policy. Okay, so this is pretty close to what you would actually want to run. However, we still need to explain exactly how you do the value backups. Okay, so I was just saying here, you have to estimate p hat and v hat, and you need to calculate this. And the tabular case is pretty straightforward, but the question is, how do you do it in the case of linear MDPs? So it's pretty well known, but in linear MDPs, P and psi are actually the size of the state space and the action space, and they're too large to actually hold in memory or calculate. But actually, we don't really want to calculate them. All we want to do is calculate these value backups. Okay, so value backup is the expectation of the value over the next state given the current state in action. So this is actually this quantity PV at X and A. Right, so you can just plug in the write this explicitly and plug in the linear parameterization. And what you'll see is that actually this next state value is simply phi at the current state in action transpose this vector V. Okay, and this vector V is given by this term. So this is just a type of linear regression. And if you change size a little bit and add V at XH plus 1, you can see that for each tuple of XH, AH, XH plus 1, we have the following equation. So the value of the next state, which you observe, is equal to the current features, which you observe, inner product with the vector V, which is what you're trying to estimate, and you don't know it yet, plus a noise term. Okay, and this noise term is simply the difference between the value and its expectation. So this is great. This is just linear regression. And essentially, our exploration will be looking at exploring V via exploring the feature space, the state action feature space. Right, so linear regression is pretty well studied, and you can just use regularized least squares regression to solve this. Okay, so the details here are not crucial. Whoever is familiar with this will look very familiar, but if you're not familiar with this, the important thing to note is that we have this matrix, this lambda kh, which will be an important quantity throughout the work. And this is sort of the covariate matrix, which is summing the entire history, and it will, in a sense, quantify how well we're exploring the system. Okay, and using this, we can calculate an estimate of the vector V, which we'll call V hat. Okay, using this equation, this is just a simple regularized least squares. And then this P hat V, which is the exactly value backup we want to estimate, is just the features transpose V hat. All right, and the nice thing that we have for this, using a self-normalized argument, which is already from Abbasi Gori from 2011, or originally for linear bandits, then you can see that the difference between the true dynamics P and P hat with respect to V at a given state action is just the features inner product with the difference between V and V hat. And you can use Cauchy-Schwarz to get to the next line, and then bound the difference between V and V hat over this weighted norm, which uses the matrix lambda kh. You can bound this using this self-normalized argument by beta times the size of V. Okay, so essentially what this means that our uncertainty looks like this beta, which is just a constant. It's a polynomial, of course, we'll care about it, but it's something that's well behaved, times the size of the value that we're trying to do backups with respect to, times this weighted feature norm. Okay, and this, again, somebody is doing a lot of linear regression, this might be very familiar, but I think it's nice to see how it sort of looks in the tabular case. Okay, so if we want to cast a linear MDP as a tabular MDP, the easiest way to do it is just to take the feature dimension D to be X times A, okay, so the states and actions, and encode the features just as one-hot vectors. Okay, so the standard basis. And if you do that and look at the matrix lambda kh, you'll just see that it's the matrix whose diagonal is the visitation counts. Okay, so each term on the diagonal is the number of times that we visited a certain state and action pair, plus 1 because of the regularization. And then again, if you look at how P hat V looks, how the value backup looks, then again, it's pretty much exactly like the tabular case. You're just averaging over the samples that you observed up to this plus 1. And this weighted feature norm is, again, the standard 1 over square root number of times that you visited the state action pair. Okay, so this is just an analog of how well you're exploring the state action feature space. Great. So now we can go back to our optimistic policy evaluation routine, which is basically the crucial component that we need to fill in to make our policy optimization algorithm complete. Okay, so what we would maybe like to do is say, okay, let's take Q hat be just the current loss, which is standard, plus the value backup, which we just suggested, minus the bonus, which is in the UCB style, will be to subtract this term, which we'll call elliptical potential. Okay, but this is basically the uncertainty that we were discussing in the previous slide. And again, V hat is just taking expectation with respect to the policy. Okay, so we can look again at this thing like the linear regression problem that I presented before. Okay, so now we have this V hat KH plus 1, okay, measured at the next state, and it's equal to the features of the current features inner product with this V hat that we're trying to find, plus some noise or not really. Okay, so this thing that we would like to be martingale noise for all of our arguments to work is not actually martingale noise because the value function V hat depends on the entire past history. Okay, so now if we want to make this filtration, then V hat will not be measurable with respect to the initial filtration, and so this thing is not actually noise. Okay, so the standard way that's already been suggested to overcome this by Jean et al. In the original work for linear MDPs is just to use a uniform convergence argument. Okay, so we will choose some value function class V. Okay, we'll talk about it later. And then we can just argue through uniform convergence that for any fixed value function in this class, what I showed you before holds. Okay, so the uncertainty, the difference between P and P hat measured with respect to a given value function V in the function class, okay, is equal to this beta, which is essentially a constant, times the size, again, of V. Okay, so it's maximal value, square root of the log covering number of the function class V, and again, the elliptical potential. Okay, so we need to control essentially the log covering and the size of V, and everything will be fine. And then we would like to argue that the actual values that we're calculating with our algorithm, V hat KH, that they reside in the function class and thus have the same guarantees. Okay, in the tabular case, you still have to argue for uniform convergence, but it's a bit simpler because you can just take uniform convergence with respect to the state and actions. Okay, so there you sort of don't have the covering number so much. You can also look at it from this perspective, and it will be like the size of the state space. All right, so let's plug this in back to our algorithm. So how would this look? So our algorithm is now, again, we're working on the optimistic policy optimization routine. So we know how to regress P hat, and now Q hat is again calculated as the losses plus this P hat V hat, which we now understand how to calculate, minus the bonus term. And so how would the analysis for this look? So there is a standard value difference claim. Okay, this is relatively well known that you can decompose the regress as the following terms. So the first term is basically the per state OMD term that we already discussed when everything is known, but now it's with respect to the Q hat. Okay, so this is analysis-wise will work exactly as the OMD, only now we have also the size of Q hat, so we also need to control this term. But as long as Q hat is bounded, this term is bounded, and we don't need to worry about it too much. Okay, next is an optimism term. Okay, so this essentially measures like the uncertainty with respect to V hat compared to our bonus, but with expectation over the policy pi star. So we'd like this to be less or equal to 0 because we can't control the uncertainty for every policy, but just usually on policy. And finally, it's the bias or policy evaluation error, which is sort of what you would expect. This is just measures the difference between our value estimates and the true value estimates of the policy pi k. Okay, so these two terms, as we showed in the previous slide, as long as v hat is indeed in our function class, okay, so they behave more or less as the size of v hat times the log covering number times this elliptical potential. Okay, but the issue is we want the optimism term to be less or equal to 0 for all times. Okay, so in the initial time, more or less, this elliptical potential will be a constant, and the covering number would be at least a constant. And so the bonus would have to cancel out at least the size of the value function. Okay, this is in order to ensure optimism. But in this case, the size of the value function, which is just the loss plus the bonus plus the next value, would be at least the bonus, roughly. Okay, this is maybe I wanted to give this disclaimer a bit earlier. In some places, I'm like glossing a little bit over like constants or indices. Something's unclear, just ask me about it. But the idea was to convey sort of the spirit of some of the arguments rather than convoluting them a little bit too much. So take the sum of the numbers with a grain of salt. All right, so yeah, the current value function would be just the size of the bonus plus the next value function, but the bonus has to be at least also the size of the value function. So overall, we have to be at least twice the size of the next value function, which means that the value function would look exponential in the decision horizon. Okay, so this is, of course, an issue for us because we want to get something which is polynomial in H and not exponential. So the sort of usual way to deal with this, and this is like almost in every like theoretical RL algorithm, is just to clip the Q function. Okay, so you just restrict it if the value exceeds plus or minus H. Sometimes you can just do it one-sided clipping. Then you just restrict it to this value. Okay, and then naturally you would get that the value is bounded. This would take care of this term. Okay, and in the tabular case, we don't have any covering number issues. So this would pretty much finish up things. But in the linear case, we still have to worry about the covering number. Okay, so this is sort of the issue that Sherman et al. Encountered and had to deal with. So let's understand what's happening here. Okay, so our optimistic policy evaluation is going to look like this. Okay, we have the Q function, which is just this sort of linear function minus this weighted norm, okay, and clipped. And our policies, because if you unravel the OMD update rule, would just be proportional to this e to the minus sum over the Q functions. And the value, again, is expectation with respect to the policy. So the Q function class is just clipping over a linear function minus this weighted norm. And this is fine. If you look at covering numbers, essentially, they are the number of parameters that you have in your function class. At least in this case, this roughly works out. And here, Q is the size D, and lambda is the size D squared. So the log covering number is about D squared for this, which is fine. But now you're getting to the policy class. Now the policy class depends on the sum over the Q functions, right? But the Q functions have this clipping argument. And so when you're looking at the sum, you can't actually combine the linear terms together. And what you'll have is that these are just, each Q function has its own parameters. And overall, you have KQ functions at the worst case. And that means that you have D times K parameters. Okay, so your log covering number will be polynomial in K. And in this case, you generally can't get the desired square root of K regret bounds. So this is pretty bad. And the value function contains in a sense, the policy class, the value function class. And so again, its covering number would be like at least as much as the policy class. So this would be bad for us. This wouldn't give us what we want. Okay, so an alternative idea is to skip the clipping. Okay, so let's maybe not clip for a moment and look at the function class. So the Q function class doesn't change much. It just doesn't have this clipping, and this just doesn't change the covering. But now when you're looking at the, I'm sorry, it's supposed to be policy class. Oh, sorry, it is okay. The policy class with respect to these Q functions. Okay, so now when you look at the sum of the Q functions, you can aggregate together the individual vectors, and and you get that you actually only have one slightly bigger vector, and so the covering number would still be about d squared. Okay, the lambda term normally would also sum and you'd have issues, but it's pretty easy to keep it sort of fixed using doubling tricks, and so this won't actually be an issue. Okay. And finally, again, the value class is just taking expectation over the Q, and you can show it pretty much the same. So it'll be d squared, also the value class covering number. So if we don't clip, we can control the covering number. However, we'll get an unbounded size of the v hat. If we do clip, we can control v hat. We can control the covering number. So this is an issue that needs to be overcome. And the question in the sort of the way that Sherman et al. Approaches, in a sense, to ask, do we actually have to bound v hat uniformly? Or can we actually only bound it for like some of the states in a sense, or over a good event? Okay, so let's go back a bit to the unclipped version. Okay, so let's suppose again that we're not clipping the Q functions. Again, we know to control the covering number, but we don't know how to control the size of v hat. But let's imagine for a second that somebody gave us this exploration data set. So the data set is just triplets of state action next state. Okay, and the data set is ensuring us that the bonuses are less or equal than 1 over h. Okay, which if you write the bonus explicitly, it's just this constant beta times h times the elliptical potential. Okay, where this matrix is only with respect to the data in the exploration data set. Okay, so this needs to be less than 1, or you can divide by beta h to get this. Okay, so if we have this data set, an easier way to look at it in the tabular setting, it just means that somebody gave you a fixed number of samples from each state and action and the decision horizon. Okay, so you could imagine that this data set should be more or less at a fixed size with respect to the number of episodes k. So far, it doesn't sound too bad. It's not a huge data set. Okay, so if we had this kind of data set, then we started our algorithm from this data set and continued. So now if we want to bound the value function, okay, then it's bounded by the loss, which is bounded by 1, okay, plus the bonus, which now we know is bounded by 1 over h, plus the expected value, the expected next state, empirical next state value. Okay, but notice that in the case of linear MDPs, p hat is not actually a valid distribution. Okay, so normally you would just bound this by the maximal p hat, but here you can't do it because p is not a valid distribution in the sense that it could have negative terms, it could sum to more than 1, so it wouldn't be correct to actually just bound it by the maximum next state value. Okay, so what you would do is just add and subtract the true dynamics, and then you would get this term with the true dynamics, where now you can't take the maximum next state value, and this is just this 1 times the maximal next state value. And again, this sort of error term, the difference between the true and estimated dynamics with respect to v hat, which is again the size of v hat, but now times h to the minus 1 because of our exploration data set. Okay, and now if you keep unrolling this, you will just get that the value is indeed bounded by 4h. Okay, so it's crucial that the bonus will be smaller than 1 over h, because if it was just smaller than, let's say, 1, then again we would have this exponential dependence. Okay, this would be 2 again. We need to keep this small in order to prevent the blow up of the value function. Okay, but is it actually reasonable to get exactly this set? So you can pretty easily imagine this kind of MDP, where there is some parts that are easy to reach, but some parts are hard to reach. Okay, so here the transition, like with k to the minus 1, you get to this branch of the MDP, and almost certainly you get to the other branch. Okay, so you would have a hard time getting samples from this part of the MDP. Okay, so obviously it would be hard to guarantee that with a small number of samples you can get this kind of data set. And so what Sherman et al. Actually suggest is instead, let's get this kind of data set. that ensures that either for a given state action and decision horizon that the bonus is bounded, or that the probability of reaching this state action at decision step H for any policy is smaller than epsilon. Okay, so now this is more reasonable, and essentially you would expect that the data set would have the size more or less of epsilon to the -1. Okay, because if you if you can reach a state with time epsilon, it'll take you about 1 over epsilon to make sure that you can't reach it. Okay, that you can't get enough samples from this state, and then you would stop searching. Okay, and actually what they show is that they can use a reward-free exploration method, which is based on an algorithm by Wagenmaker et al., and exactly obtain this kind of exploration data set. Okay, so now that you have this exploration data set, their algorithm would look at the following. First, they would do this reward-free warm-up, okay, and then the model estimation as usual, and they would augment the optimistic value estimation or optimistic policy evaluation by doing this kind of indicator clipping of the Q function. Okay, and let's look at what this will do for our analysis. Okay, so now if we're at a state where the exploration is good, okay, if we're at a good state, then the indicator doesn't do anything, but we also know from what I just showed you that we can bound the value function. Okay, but on the other hand, if we're in a bad state, then this indicator will just zero out the Q function, and then the value function will be 0, and we can still bound it. Okay, this is sort of a rough way to state it, but you can show this properly using induction. Okay, so this sort of clipping, at least on the good event that the least squares regression holds, is going to give us that the value function is bounded like we wanted. Okay, but on the other hand, because this term is sort of fixed and it depends on the state in action, now that we're looking at our policy class and we depend on the sum of the Q functions, then again we can put the sum inside the linear term, okay, and aggregate the linear terms together. Again, you would need to keep this lambda at least partially fixed, but this is already fixed, and so you can keep it outside of the sum. Okay, so again, you have a small number of parameters, and indeed what they get with their method is that they have both the bounded value estimates that they need and a small covering number. And this basically, from there, the analysis actually works. Okay, so what does this kind of clipping cost them? What do they have to pay? Okay, so if we go back to our analysis, okay, then we still have the OMD term, which is exactly the same. Okay, but the optimism term, now we need to use total expectation to split it into the expectation given that we're in the good states, meaning where we have good exploration. Okay, and here we just get the standard optimism. Okay, again, for the bias as well. And the bias will work just like the previous analysis that I showed. But what you will pay for this, okay, is that the other part of the total expectation is basically that the probability that you're in a bad state. So from the bias term, you would get the probability with respect to playing pi k. Okay, and from the optimism term, you would get the probability with respect to paying pi star. Okay, but because the exploration data set ensures that the bad states are reached with probability epsilon uniformly over policies, then this also holds for pi star as well. So each of these terms is just epsilon, and the overall cost of doing this indicator truncation is just epsilon times k. Okay, and h and d, and there are many other factors, but like with respect to k, this is the dominant term. Okay, but on the other hand, we also have this warm-up in the beginning, and like I explained roughly, this would take epsilon to the -1 rounds of doing this warm-up to get the initial data set. Okay, so overall, you can choose epsilon to be about 1 over square root of k, and this will balance out these terms to give you overall square root of k. Okay, so overall, Sherman et al.'s method achieved the desired square root of k regret. However, they they need this kind of reward-free exploration mechanism in the beginning, which requires them to have sort of uniform exploration over all the policies. Maybe because of that, they get not the ideal dependence on D and H, at least considering this is a non-variance reduced algorithm, they don't achieve what you would maybe hope to get. And above everything else, the reward-free algorithm is very complex. It's very delicate. It's based on first-order methods and using Catoni estimators, and it's not clear that it's actually crucial to have this. And maybe just as an example of the uniform exploration issue, so if you look at this MDP, then yeah, it's very hard to reach this branch of the MDP, which you would maybe take a lot of time to discover when you're doing reward-free exploration. But when you're doing reward-aware exploration, you can see that the loss here is very large in the beginning. And so actually going to this branch would give you a lot of loss anyway. So when you're reward-aware or loss-aware, you would maybe discover that it's maybe not worth investing in this branch anyway. So it's sort of more of a conceptual advantage, I would say. Cool. So can we do better? We're in this talk, so probably yes. Right. So before we explain what we want to do, I thought of sort of, I think, nice way to visualize what's happening in Sherman et al.'s algorithm. So in a sense, they're saying, okay, this is our original MDP, and yeah, some parts of it are hard to reach. We're going to do this sort of warm-up routine, which will take us some time, some non-negligible time. And after this warm-up routine, we'll forget that this is the original MDP, and from now on, we'll imagine that the true MDP looks like this. We'll be throwing out sort of all of the branches that are hard to reach, all of the state actions that are hard to reach. And sort of this is what I call, in a sense, the contracted MDP. This is not really an MDP in a sense, because in some places the probability doesn't sum to 1, like you sort of go into the ether at this point. And from a practical sense, when you sort of step off the contracted MDP, you just play random. And this is also what like the math would entail eventually. Okay, so they sort of invest a bulk sum time, like an initial upfront investment, and find sort of this MDP where all the states are reasonably reachable. Okay, and what we suggest essentially in our work here is to do this more in a gradual way and in a reward or loss aware way. So initially, when you have no data, you would have to contract the MDP to a singleton. Okay, so the only way you can guarantee anything is essentially if you shrink the MDP to nothing. Okay, so now the bonuses over this sort of null MDP would be bounded because you contracted them with this indicator function. But obviously, this is very far from the real MDP. But then, like the math would behave correctly, and you would gain some exploration. We showed this is optimistic in a sense, and so you would have some exploration. Eventually, you'll have enough exploration to say, okay, now I can guarantee that the bonuses are small for this part of the MDP, and I would uncontract a little bit of it. Okay, and I will continue to do this as I play in a reward-aware way. And so when I see this kind of branch where it's hopeless to explore here anyway, I won't continue exploring, but I would uncontract whatever parts of the MDP that I already discovered. Okay, any place that is easy to reach and is worth reaching. And this is sort of the idea of our method, to just do this gradually. So again, it's worth noting that these are all sub-MDPs, which is just to say that the transition probabilities are sub-probabilities, meaning they're still positive, but they sum to less or equal to 1. And basically, all of the standard math of MDPs pretty much works as is for this case. Like, as long as things sum to less or equal to 1, not more than 1, then this is fine. Again, we'll play random when we step out of the contracted parts. And importantly, we'll see that this is, again, an optimistic operation. Okay, so how does our algorithm work? So starting out from Sherman et al. Algorithm, we're going to be removing the reward-free warm-up. So this is not going to happen anymore. Okay, and this this indicator term that's used for clipping, which was with the original full data set, okay, will now be with respect to the current data set that we're holding. Okay, so this is a relatively minor change to most of the algorithm, but importantly, get rid of the reward-free warm-up. Okay, so let's go through it. At each episode, we're given a policy, and we're going to do this optimistic policy evaluation, okay, by calculating again this Q hat, just as using the linear regression for the V hats and reducing the usual bonus, but multiplying everything by this indicator. We're now we're going to use the lambda kh of the current episode, okay, and the value again is expectation with respect to the policy, and we're going to use the Q hats to just do OMD per state. And this gives us a stochastic policy. Some technical details that I'm glossing. One, for technical purposes, we'll have to replace this indicator with smooth version, so it's going to be some sigmoid. But again, pretty purely technical. It's not going to matter much. And the second thing is we're going to need epochs. This is also actually something that's needed in Sherman et al. Algorithm. So this is not, it's basically the same for slightly different reasons, I would say. But basically, you use the standard doubling trick on the matrix lambda kh. So you only update it a logarithmic number of times. All right, so this is our algorithm. And what's written here is exactly what was written in the previous slide, but just rewritten in a way that will be sort of more conducive to the way that we'll want to analyze it. Okay, so I just took the indicator from the function Q hat, okay, and redefined the features. So I call these the contracted features, okay, and they're just the original features multiplied by this indicator function, okay, which essentially says that if we have explored this state action sufficiently, then this is just the normal features. And if we did not, then we take these features to be 0. Okay, and again, in practice, we'll replace this with a smooth version of this function. But it'll smooth, but it's still very quickly transitioning, this kind of sigmoid. So morally, it will say the same. Okay, and this is basically the full algorithm up to, again, the smoothing and the epochs. Pretty simple, without any like hidden subroutines or reward-free warm-ups or anything else. I think I skipped a few slides. Give me a second. No, sorry, I'm okay. Okay, so sort of in the sense that we kept the algorithm almost the same. Okay, and again, we still have this indicator, which in a sense operates exactly like what we had in Sherman et al.'s algorithm. So the sort of boundedness of V hat and the boundedness of the function class would follow using roughly similar arguments. Okay, so sort of in a sense, our contracted features policy optimization ensure these things in a similar way to what happens in Sherman et al. But the question is, what kind of cost do you pay for this? Obviously, we removed a pretty big part with the reward-free exploration phase. Okay, so sort of the way that you would naively think of analyzing this is if we start from what Sherman et al. Did. This is exactly the decomposition that we looked at before. The OMD term is fine. The optimism term is again fine because we're conditioning on the good states, and so is the bias. But what we're paying for is, again, the sort of probability that we're in bad states with respect to both the policy pi k, our policy, which will be okay, but also with respect to pi star. So using our truncation, because we don't have the sort of uniform exploration phase, then these terms will actually turn out to be these kind of elliptical potential terms, these probabilities. Not exactly probabilities, but if you do sort of the equivalent thing, this is what you'll end up with. And the issue is that now you have this elliptical potential, but with respect to pi star. And it's pretty well known and it's pretty sensible that this is your uncertainty. And you know that on policy, you're going to shrink your uncertainty constantly. And so this term with pi k will behave nicely. But this term with pi star is something that we don't know how to control. So this is not going to end up well. You need to do something else. Okay, so to understand what we want to do, we'll just define this relatively simple notion of contracted MDPs. Okay, so for contracted MDP, we just started with an initial MDP, okay, with losses L and transition P. And you have contraction coefficients, rho H of X and A, which just need to be between 0 and 1. And for this, you can define contracted, again, sub-MDP, because things will sum to less than 1. Okay, where you just take the transition function and multiply it with the contraction coefficients and also the losses. Okay, and what's relatively straightforward to see from this, that this is an optimistic operation. Okay, so this is losses, you're just shrinking everything. So for any policy that you take, its contracted value will be smaller than its true value on the MDP. Okay, and if you take this notion to linear MDPs, so in linear MDPs, you have the thetas, the psi, and the phis. Okay, and again, you have the contraction coefficients. So the contracted linear sub-MDP, okay, is keeping the thetas and the psi the same, and is only contracting the features. This is sort of a pretty nice and compact way to put it. And again, this is completely equivalent to the tabular case that I showed in the previous slide. So we, again, have optimism. Okay, and the other thing that we have is if we take the contraction coefficients to be this indicator that we have sufficient exploration, like we do in our algorithm, then what you have is this pretty simple lemma that the difference between the features and the contracted features, okay, projected on a vector v, which essentially will be exactly, this is like our, this will be our p, yeah, this will be like PV, like the expected next value, and this will be the contracted expected next value. Okay, then it's less or equal to the square of the elliptical potential. Okay, so the choice of square here is pretty arbitrary. The proof is pretty much a one line. Okay, so if you look at this difference, it's just the actual features times the complement of this indicator. Okay, and the complement of this indicator is pretty trivially bound by this term, or this term squared, or this term to cubed, or whatever you want. And basically, the choice of square is sort of the nice thing to get. Like if you want to get a sort of low order term, you would take this. If you assume that the number of episodes is relatively the dominant term, that this would be like the best choice. Is this part clear? Because I think this is like the crutch to understanding everything else. Cool.
Yeah,
okay, so
I guess I'm wondering about the role of the choice of the square here. So you say that this can be like any power that is greater than 1, or
yeah. I can explain this later. Basically, yeah. I mean, not can. I will explain this later in a sense. Essentially, you're just going to pay the sum of this term. So you can take like without the square, and then this like sort of this term will sum to square root of k. But you can also just the same take this square, and then you would get log k. You're going to pay for this in d and h factors. So it sort of depends what you're assuming the relationship between dh and k is. Okay, so in a sense, if d and h are close to k, then it would be more sensible to take this as 1. Okay, but you can sort of, I'm not actually, I'm pretty sure that this is like purely in the analysis. You don't actually have to fine tune your parameters according to this, not 100%, but you can basically choose how to do it in the analysis. But in the end, I'll mention sort of an additional nice point of why you would maybe consider choosing this as a square. Okay, so we'll get back to this term in a minute. Let's see how things look out now that we have this contracted MDP. Okay, so recall we have our regret. The regret is simply the difference between the value of our policies and the value of the optimal policy, which is like best in hindsight. Okay, but like we mentioned, the contraction is an optimistic operation. Okay, so we can move from the value of the optimal policy to the contracted value of the optimal policy. Again, here the contraction actually like changes with time with the epochs. So I'm hiding a bit of the like technical math, but this is essentially what you're doing. You also need to split like into epochs, but this is just technical. Okay, so all you did is do this operation, which is again, this contracted value is just closer to 0. So this is like a smaller value. You're only increasing the regret. Okay, and now if you do the sort of the standard value difference lemma, but notice that you're starting here with respect to the contracted MDP and not with respect to the true MDP, you would get a slightly different decomposition. Like this is the original decomposition. Okay, so you have the OMD term, okay, the optimism and the bias, okay, and the okay, and after this modification, after first moving to the contracted MDP with respect to pi star, then this decomposition changes as follows. These expectations, which before were with respect to the with respect to the true MDP, are now with respect to the contracted MDP. Okay, this is just like not good, but it's not very bad. So we can manage this. Okay, but the other thing that you get is now this error, because you started out from the contracted MDP. Okay, then this P tilde is basically the contracted empirical transitions. Okay, so you contract sort of your empirical linear MDP. So if P hat before was just our features transpose the V hat that we got from the regression, then P tilde V hat is the same, but contracting the features. Okay, so this is over the contracted empirical MDP. And this we would get anyway, but because we did the transition in the previous slide, we measure now the difference to the contracted true MDP and not to the full MDP. Okay, and this is essentially amounts to the conditioning that we had before on being in the good states and being in the well-explored states. Okay, because before we were doing, like if we had the full MDP here, then we also get the difference, like the difference on states that weren't explored well enough would not be 0. Okay, but here both of these are contracted. So on the bad states, this is just trivially 0. Okay, and on the good states, you get that this is bounded. Okay, and in the bias term, it actually stays the same. You just get this, again, the contracted features. And what you can do for this is because you have here the true MDP, then sort of in the way that Sherman et al. Did, you just add and subtract the contracted transitions. Okay, and then this term is sort of, again, the equivalent of the conditioning on the good states. And this term is exactly what we showed from the previous lemma. Okay, it's the difference between the true and contracted MDP. It's just these features measured on a value function. And so we can bound it with the square elliptical potential. And using standard arguments, you can show that this is like logarithmic in K and polynomial in H and D. Okay, so if we chose to take this to the power of 1, we get square root of K here. And like the terms of H and D, I think would be maybe a little bit higher. So you'd get slightly worse dependence on H and D in the overall regret, like in the leading terms for the square root of K. Okay, and again, the main, like the point here is now because we sort of already preconditioned on being in the good states with respect to pi star, we're only paying for like the on policy truncation. Okay, we don't have this term which is with respect to pi star like we had before. This is sort of the key ingredient for making the analysis work. Okay, and the remaining terms are pretty much the same as it was before. Like from here, this sort of continues the same as it was for Sherman et al. Okay, so overall, if you combine everything, you'd get the aforementioned regret. You get square root of K maximum between D to the power of 3, H to the 4th, to D times H to the power of 5. And again, this is just the entire algorithm up to epochs and smoothing. Any questions about it before I move to discussing a few like final points?
No, it's all perfectly fine. Yeah.
Cool. So some like afterthoughts, I would say. Did we actually like need to clip things? So I think sort of taking it for granted in MDPs for the most part. In RL, you have to clip. But let's for a second forget about clipping. Let's say, again, we're going back to not clipping. Okay, so this is just, again, the vanilla case. Everything is the same, just no clipping, no indicators, no nothing. There will be some epoch schedule, again, for the model regression. Okay, so now if we look at the standard decomposition, this is like the usual value difference lemma, but you can change the roles of the way that you do the value difference lemma. Okay, so if you change them, then you would get the expectations with respect to the empirical dynamics in this in the OMD and optimism term. But what you would get in turn is that instead of having the empirical value function in the optimism, you would get like the true optimal value function. Okay, so this is the benefit that you're getting. And now this term is easy to bound, like V star is a constant. It's not something that's data dependent. And so now you can use standard arguments to bound this. Okay, now you can easily choose your bonus and make the optimism term less or equal to 0. And then this next term, which is the usual bias, this one didn't change at all. Like it only affected the OMD and optimism term. Then now, because the bonus is not dependent on the size of V hat, then it's relatively easy to see that A, we don't have clipping, so the log covering is bounded. And B, we can bound V hat just by like 1 plus the, sorry, okay. And now if you look at the tabular case at least, then you can bound V hat by doing just like 1, which bounds the loss, plus the bonus, plus the expected next value. And in the tabular case, P hat is a valid distribution, so you can bound it with the maximal next state value. And then you can just unravel this and get that you indeed can bound V hat. Okay, so in the tabular case, things actually work out. Things are fine. Okay, but what does happen is that when you're going to try this in linear MDPs, then again, P hat is not a valid distribution. So first, like the previous argument for bounding V hat doesn't work, but actually, like even worse things break down. So when you look at these expectations, now they're with respect to something which is not a distribution, and it's bad in both senses. So first of all, you have negative terms. So now it's not clear. You don't need to bound this to be less or equal to 0. You sort of need to bound the inner argument to be less or equal to 0 in absolute value. And this is usually hard to do, but actually you can do it if you use random bonuses. This is actually, you can overcome this. But in the OMD term, I don't know how we sort of need to have this absolute value of the regret bounded. And like there are some claims on FTRL that can be non-negative and stuff like that, but I'm not sure how to do it. And even then, it would fail because things are still summing to more than 1. So it can explode. Again, in the dimension H. So, and more generally, like when I was trying to look at it, it seems like I didn't prove it, but it seems that the sort of the planning problem when you're trying, you have samples of a linear MDP, and you're trying to do planning in the empirical MDP, it looks to be like a hard problem, like it's non-convex, because you sort of lose this positivity constraint if you're trying to calculate the occupancy measure set. So eventually this argument does break down in linear MDPs, but I thought it's nice to know that it does work in the tabular case and why it doesn't work in the linear MDP case. Final slide. So I mentioned why it might be nice to look at the square. So if you look at the case of bandit feedback in the work of Liu et al., they get k to the 3/4, but let's imagine that they would try to get square root of k. So one part of their algorithm, it's debatable if it's necessary or not, is that instead of the usual bonuses, they use this kind of linear bonuses. Okay, or they're the square of the usual bonuses, and what it gives you is that the bonuses are linear in the parameter, or linear in lambda. Okay, and then you can sum them, and the covering number remains nice. But the issue is when you use linear bonuses, is the way you get to them is you use this like AMGM on the original bonuses. Okay, and you get this additional constant term that will sum over k, and so you have to keep it small enough. Okay, so to keep this term small enough, you would have to have the coefficient of the elliptical potential in the bonuses be about square root of k. Okay, now if you want to control this entire bonus to be less or equal to 1, then you need the initial bonus to be like you need significantly more exploration. So if you try to do the reward-free warm-up that Sherman et al. Use, because this is now square root of k, you would need like k episodes of reward-free warm-up, which obviously would give you linear regret. And because we have this squared elliptical potential, then if you use our method, then again, this will sum to log k, and now the beta squared will be square root of k. Okay, so you will actually get that you can get the bonuses to be small enough using our contraction method. So this sort of solves one potential issue that they have in the algorithm, but like a remaining significant challenge is how to estimate the feature covariance in order to do importance sampling. And for this, we're not sure how to do that yet. Like something we definitely tried thinking about, but it's an interesting open direction. And that's it.
All right, amazing.
Great. Thanks a lot.
Oh yeah. Okay.
Record, maybe.